Okay, we're going to cover some things for 30.3, simplifying radical expressions. And the one thing I want you to do somewhere in your notebook, somewhere on a chart, maybe take a screenshot of what I have here or something, but you should in general be familiar with like all of the squares up to maybe 13 squared. Like 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, and so forth. And just, if you don't know them, make a list of them to have on hand. And then 1 to the third power, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, and so on. And then the fourths you might want to do as well. We don't generally go bigger than that. If we do fifths, usually it's like 1 to the 5th power, which is 1, and 2 to the 5th power, which is 32. I don't know what 3 to the 5th power is, but generally we stick with these, okay? So having said that, if you come up here, this first one, the cube root of 40, well, there's no cube roots. Let's go down here at the list. There's no cube roots that equal 40. So what you want to do is look at the list and go, is there a number here that fits into 40? That is a perfect cube. 8 goes into 40. So what we're going to do is go back up here and we're going to rewrite this as the cube root of 8 times the cube root of 5, because 5 times 8 is 40. Because the 8 part we can solve. The cube root of 8, we're saying what number had an exponent of 3 that made 8? This part is 2. The answer is 2. But this part we can't solve. So it's 2 times the cube root of 5. That's simplified as far as it can go. This would be our answer. So come to the next one. The square root of 50. Well, again, we don't have any squares that equal exactly 50. But when you look through the list of perfect squares, do you see any numbers that go into 50 evenly? And right here it is. 25 goes into 50 evenly. So we know we can find the square root of 25, which is 5. So we'll come back up here. We'll rewrite this as the square root of 25 times the square root of 2, because 25 times 2 gives us 50. This part we can solve. The square root of 25 is just 5. So it's 5 times the square root of 2. This part we couldn't solve, so that's our answer. We go as far as we can. Excuse me. So this one's saying the cube root of something. 56, and let's go down here and look at the cubes. Any of these numbers go into 56? Yeah, 8 goes into 56 because 8 times 7 is 56. So the cube root of 8 is 2. So we would say the cube root of 56, the cube root of 8 times the cube root of 7 for that part, okay? So the cube root of 8 is 2, and that still leaves us with the cube root of 7 that we cannot solve. And then we have to ask, are there any cubes here that we can pull sets of a to the third out of here? And there isn't, so that part's not solvable. So our answer is 2 times the cube root of 7a squared. Okay, here we go. This one, it's square root since they don't show an index. You know, up here I wrote a 2 there, but that's not normal. We don't usually put a 2 there. We assume there's a 2 there. So we're assuming we're looking at square roots. And so the question is, any sets of x squared in here? Well, yeah, there's 3 sets of x squared because x to the 6th. That would be 6 x's. So I could break it down actually. I could break it down and go, well, there's x squared times x squared times x squared times x. That would be the long way to write it out. And then with the y's, I could say, yep, I have y squared and y squared and y squared and y squared. I have 5 sets of them with a single one left over. So for each one of these, the square root of x squared is x. Square root of x squared is x. So I have 1, 2, 3 sets of these. So I would say I have x to the third power as the answer for this part of it, with a single x left over that has to stay in the radical because I can't find the root of it. And then here I have 1, 2, 3, 4, 5 sets of y squared, so that means I have y to the 5th power with a single y left over. So that's how we would get this. Over here, the square root of 81, sure enough, 81, the square root of 81 is 9. So we know we can find the square root of 81, which is 9, and when it comes on the outside, we drop the radical. When we're able to solve it, we don't have to keep the radical symbol. Now I need to know how many sets of x squared do I have? Well, I have 3 sets of them, with 1 set left over that we can't find 2 x's to solve that part, because that was x squared times x squared times x squared times x. That's 7 x's now. So that's how this became the answer. So now I believe we just have 2 more left to do here. Okay, so 32, we're doing square root, 32 y to the 5th w. Well, there is no square root of 32. If you look back over here, none of these are 32. However, 2 numbers go into 32. 4 goes into 32, and so does 16. You always want to make sure you choose the biggest one, okay? So we can say the square root of 16 times the square root of 2 is what makes 32. Square root of 16 is 4, so it doesn't need the radical because we were able to solve it. But inside the radical, we got to keep the 2. How many sets of y squared can you get out of y to the 5th? Well, we can get 2 sets of them with 1 left over. And then how many sets of w squared do we have? We don't have any, so that w has to stay inside here. So there's your answer. And then lastly, this is to the 4th root. We're looking for 4th roots here. And I'm going to go quick down to my list real quick. Do you see 256 in my list? Sure enough, there it is. 4 to the 4th power, or the 4th root of 256 is 4. So the 4th root of 256 is 4. That can come outside the radical. Do we have any sets of k to the 4th? No. So we're going to have to keep that k inside of here. There's 11 p's here, so we do have some sets of 4. We have p to the 4th times p to the 4th times p to the 3rd, because 4 and 4 is 8 plus 3 is 11. So we have 2 sets of p to the 4th, which means we can solve that and say p to the 2nd, 2 sets of it, with p to the 3rd left inside because we can't make another set of 4.